Hi, welcome to Frequentists versus Bayesians. Okay, so the topic of this video is the use of Bayesian versus frequentist statistical methods in the reporting of scientific results. That might not sound so exciting, but don't go just yet. It's a surprisingly controversial topic, and people can have very strong opinions about how scientific results should be presented. It's also the case that knowing the difference between Bayesian and frequentist reasoning can prevent a lot of common misunderstandings about the interpretation of scientific results. In particular, a lot of results are presented in frequentist terms, but are often incorrectly interpreted by the reader as Bayesian statements. As a bonus, there is a link to an xkcd comic about frequentists versus Bayesians in the video description below. If you don't understand that comic, but would like to, this video will hopefully clear some things up. But if it doesn't, feel free to ask questions. Okay, so for this video, it will help if you know a bit about Gaussian errors and hypothesis testing. But we'll try to explain things as necessary as we go. Nonetheless, after this video, you might want to check out the hypothesis testing playlist, especially the videos called What's a P-Value and Statistical Significance. You might also want to take a look at the playlist Minicourse on error bars, measurements, and decision analysis. Okay, so first we should talk just a little bit about the scientific method. Let's say we have some natural phenomenon which we wish to explain. That will be represented by this tree. We form a hypothesis to explain this phenomenon. This hypothesis is represented by this aha moment. This hypothesis will make predictions about nature which we can experimentally test. These experimental tests typically involve measuring some quantity. This measurement is of some interesting quantity, which could be, for example, the lifetime of a particle or the rate of a disease in a certain population. But there is a complication. Due to measurement error, the measured value of this quantity will not equal its true value. So, we need to understand what the measured result tells us about the hypothesis that we're interested in. For example, say a particular physics model predicts that the mass of a certain particle is 435 GeV over c squared. We measure the mass of the particle and actually get 457 plus or minus 11 GeV over c squared, where we're taking the errors to be Gaussian distributed. What consequences does this measurement have for that particular physics model? Well, it depends on the specific question you're asking. Frequentist and Bayesian statistical methods make different statements about results like this one. Okay, so let's look at questions frequentists and Bayesians do or do not ask. Roughly speaking, the difference between frequentist and Bayesian statements is the following. A frequentist asks, under the given hypothesis, how unusual is the observed result? A Bayesian, however, asks, given the observed result, what is the probability that the hypothesis is true? And in particular, we should explicitly state that the type of question asked by the Bayesian is not asked by the frequentist. Okay, let's look at the frequentist perspective first. Let's go back to our particle mass example, where we said that our measured result was 457 plus or minus 11 GeV over c squared, and where we were assuming Gaussian errors. We had a model that predicted the mass was 435 GeV over c squared. So let's ask, what does the frequentist say in this scenario? Okay, we said we're assuming Gaussian errors. This means that the measured mass, m measured, will be Gaussian distributed around the true mass, m true. This Gaussian will have a standard deviation of sigma. If the experiment were repeated in many independent trials, 95% of the time, m measured would land within about 2 sigma, actually more like 1.96 sigma, of m true. Okay, so our hypothesis predicted that the mass would be 435 GeV over c squared. M measured was reported as 457 plus or minus 11 GeV over c squared. This result means that the value observed was 457 GeV over c squared, and sigma is 11 GeV over c squared. So we can see that the measured value is 2 sigma above the hypothesis prediction. If m true really were 435 GeV over c squared, then 95% of trials would give results closer to 435 GeV over c squared than this one did. So what would a frequentist say about this? They would say that under the hypothesis that the mass is 435 GeV over c squared, this is a somewhat unusual result. Under that hypothesis, 95% of trials would land closer to 435 GeV over c squared than this one did. If you're using a significance level alpha equal to 0.05, then we would exclude the hypothesis that the mass equals 435 GeV over c squared. We should note that here, saying that alpha is equal to 0.05 is just another way of saying that we choose to exclude the hypothesis if the measured result falls farther from the prediction than 95% of trials would. Alpha equals 0.05 is a fairly common choice. Well, okay, that's what the frequentist said, but we'd like to know the true mass of the particle. We can't get an exact answer, but perhaps we'd like to know the probability that the true value of the mass is in a certain range. So, let's say we ask a frequentist, what's the probability that the true value of the mass is between 450 and 460 GeV over c squared? The frequentist responds, not my job. Ask a Bayesian. Okay, so let's take that same question to a Bayesian. We ask, what's the probability that the true value of the mass is between 450 and 460 GeV over c squared? Well, since most results in particle physics are presented using frequentist methods, they're probably just happy to see you. But then they say, it depends on your prior. So what does this mean? Priors are assumptions that you have to put in about probabilities before you look at your experimental data. They are subjective, and not everyone will agree on the proper choice of priors. The answer that the Bayesian would give you about the probability that the true value of the mass is between 450 GeV over c squared and 460 GeV over c squared depends on both the experimental result and the subjective prior. As there isn't a single correct choice of prior, reporting results using Bayesian methods is not so straightforward. In fact, our particle mass example is a little too complicated for our purposes here. Let's choose a really simple example to illustrate the difference between frequentist and Bayesian methods. Okay, so here's the example we'll work with. A random person walks up to a frequentist. They say, "I just bought this novelty coin. It always comes up heads." The frequentist responds. They say, "Interesting. Naively, I would guess that it's a fair coin. But perhaps it can be biased to usually come up heads. Toss it 5 times. We'll take the number of heads as our test statistic. I'll reject the fair coin hypothesis if the p-value is less than 5%. Okay, let's explain what those words meant. A test statistic is a quantity calculated from the dataset to distinguish different hypotheses. Here, the number of flips coming up heads is our test statistic. This should distinguish between a fair and a weighted coin. A p-value is the probability, under the null hypothesis, of obtaining a result at least as extreme as that seen in the actual dataset. Here, the null hypothesis is the fair coin hypothesis. Okay, so they flip the coin 5 times, and it comes up heads all 5 times. If the coin was fair, the probability of this occurring was 1/2 to the 5th power, or 1/32, which is about 3%. The p-value is defined to be the probability of getting a result as extreme or more extreme than that seen in reality. In this case, extremeness is defined by how many flips came up heads. Here, there isn't any possible more extreme event than what was seen. Every coin flip came up heads. So this 3% is the p-value. Conversely, the probability that at least one flip would have come up tails is 1 minus this, or about 97%. So the frequentist responds, "Okay, I reject the fair coin hypothesis." The person asks, "So it's probably not a fair coin then?" And the frequentist says, "I didn't say that." A frequentist doesn't make a statement about the probability of a hypothesis, only about how strange the result is if the hypothesis is true. The strangeness is quantified by the p-value, the probability to get a result as extreme or more extreme than the one actually observed. Okay, so now let's imagine that the person with the coin had instead walked up to a Bayesian. Again, they bought the coin believing that it always comes up heads. The Bayesian responds, "I have seen this hundreds of times before. People buy these novelty coins thinking they work. Every time they turn out to be normal, fair coins. I will generously put the probability that you're right at 1%. So the person flips the coin 5 times, and it comes up heads all 5 times. If the coin was fair, the probability of this occurring would be, as before, 1 over 32, or about 3%. The Bayesian sees this and responds, "It's probably a fair coin." Okay, so why does the Bayesian say this? The Bayesian looks at the obtained result and considers the probability of that result under the relevant hypotheses. The Bayesian takes as a prior that the probability that the coin truly does always come up heads as 1%, and the probability that it is fair at 99%. Let's say this scenario was repeated many, many times. In 1% of trials, the coin truly is a coin that only comes up heads. In all of these trials, the coin comes up heads all 5 times. On the other hand, in 99% of trials, it is a fair coin. In 1/32 of these trials, it comes up heads all 5 times. So, let's look at the 2 ways the coin can come up heads all 5 times and their probabilities. The coin can be a fair coin, but by chance come up heads all 5 times. The probability of this is 99% times 1 over 32, which gives 3.1%. Alternatively, the coin can be a heads-only coin. This has a probability of 1%. If it's a heads-only coin, it will come up heads 5 times with 100% probability. We add these together to get the total probability that the coin will come up heads all 5 times. That is 4.1%. Okay, so here are those results from the previous slide. In a total of 4.1% of trials, the coin would come up heads 5 times. 3.1% of that 4.1% is when the coin is fair, and 1% of that 4.1% is when the coin is heads only. So, to get the probabilities after the flips of the 2 hypotheses, we divide by the 4.1%. The probability that the coin is fair is 3.1% over 4.1%, or about 76%. The probability that it is heads only is 1% over 4.1%, or about 24%. The person looks confused. They ask, "But aren't 5 heads in a row very unlikely for a fair coin?" The Bayesian responds, "Sure, it's an unusual result, but the probability of that unusual result is larger than the prior probability that you bought a heads-only coin." Okay, let's discuss what we've seen a bit. Bayesian methods ask the questions that we want answers to. If we measure the mass of the Higgs boson, we want to know the mass of the Higgs boson. So the question, what's the probability the mass of the Higgs boson is between 125.3 and 125.7 GeV over c squared, is a question a Bayesian can address. However, frequentist methods ask questions that are more straightforward to answer. For example, if the mass of the Higgs is 125.65 GeV over c squared, how strange is a particular experimental result? That's a frequentist question. But Bayesian reasoning requires a prior. Remember in our coin flipping example that the Bayesian applied a prior probability of 1% to the heads-only coin hypothesis. If they had been more generous in their estimate, and instead said 5%, the answer would have been different. You might know the phrase, extraordinary claims require extraordinary evidence. Extraordinary claims are those with small prior probabilities. So this phrase is a Bayesian statement. As a last note, we should point out that the frequentist strategy is not entirely immune to subjectivity either. Different people may make different choices of test statistic, and this will affect the result. Although for reasonable choices of test statistic, hopefully this choice won't matter that much. Okay, so for more information, you might want to take a look at the videos mentioned at the beginning of the video. And additionally, you might also be interested in the Bayesian playlist, as well as the playlist called Coin Flipping Bayesian Probabilities and Priors. So go check those out.